Thank you, Professor. It's a topic. My name is Muhammad Noman, and I am a PhD student under the supervision of Professor Jeju. And the topic of my presentation is sea urchin shaped hierarchical cobalt carbonate hydroxide hydrate PANI nanocomposite with enhanced activity for asymmetric supercapacitor. So introduction and background of the study is that because of increased urban industrialization and population growth, the demand of energy storage devices has increased. And this issue has attracted the attention of scientific community to investigate new energy storage and energy harvesting devices. The problem with energy harvesting and energy storage, particularly energy storage devices, we call about supercapacitors. And in supercapacitors, the asymmetric supercapacitors, the energy density and power density are the key factors. And if we can increase the energy density and power density of these devices, it means that we can store maximum amount of energy. So by keeping this idea in our mind, we decided to investigate new materials, and we synthesized a material which is called cobalt carbonate hydroxide hydrate, and we made a composite with polyethylene, and we then synthesized the combination of these two materials. We synthesized a nanocomposite, and then we use this composite for asymmetric supercapacitor application. So this is the synthesis process of materials and electrode fabrication for supercapacitor device. This is the schematic representation that how we mix the urea and cobalt nitrate as that hexahydrate as a precursor, and that we carried out a salvothermal treatment followed by centrifugation and drying to form the uh, nanocomposite. And meanwhile, we also added the polyaniline in the autoclave so that the polyaniline and cobalt carbonate hydroxide hydrate can so both the particles can join together to form the nanocomposite. After making the nanocomposite, what we made the electrode for the supercapacitor testing, and for the supercapacitor testing, the slurry preparation was carried out on hot plate, followed by deposition on nickel foam, and then the nickel foam, the three electrode assembly was used to investigate the electrochemical energy storage performance. This is the structural characterization of the synthesized material. This is the XRD of the four compositions in which we added. Actually, we synthesized the cobalt carbonate hydroxide hydrate, and then we added the polyaniline in various concentrations, 10 milligram, 20 milligram, and 30 milligram to find out the optimized value. And this is the XRD pattern of polyaniline and all the compositions, and the clear peaks for the addition of polyaniline, and the clear peaks for the identification of the planes for cobalt carbonate hydroxides hydrate are shown over here. Similarly, the FTIR spectra to find out the functionalities of the nanocomposite FTIR analysis was performed, and to compare the D spacing and the G band of the material, the Raman spectra of the nanocomposite was also performed to find out that how the material is porous and how much charge it can accommodate in itself. The BET analysis was performed, and it is these two graphs showing the BET analysis of the material. If we talk about that SEM, TEM, SEM, and EDX analysis, very clear we can see that this picture shows the sea urchin shape morphology in which the needles are coming out of the spherical core, and this is the more zoomed TEM image in which we can see the edges of the needles, and that this picture shows the distribution of funny particles inside the material. So SEM analysis also showed similar kind of morphology, and EDX analysis also showed that the carbon, oxygen, and cobalt, the key elements of our materials, precursor materials, are found in all the samples. And in 30 milligram addition of polyaniline, the maximum amount of carbon was found. After this, performing the structural characterization, then we check our material for electrochemical energy storage device. As discussed previously, that we for the electrode electrochemical testing we use the three electrode assembly, And this is the cyclic voltammetry curve of the maximum results, showing material that was 20 milligram addition of polyaniline in cobalt carbonate hydroxide hydrate. This is the comparison of all the samples. We can see that the 20 milligram addition of polyaniline showing the maximum area under the curve, and it means that the maximum charge it can accommodate. This is the cyclic galvanostatic charge discharge of the material. We can show the maximum results, and this is the comparison of the all the samples, which shows that the discharge time for 20 milligram addition of polyaniline is maximum, which is in good comparison with the cyclic voltammetry. And this is the specific capacitance tension with respect to changing the applied current. At various currents, the capacitance changes. At high currents, the capacitance becomes low because the ions do not find the proper time to adjust themselves. So to find out the electrochemical impedance of the material and the electrolyte, the electrochemical impedance spectroscopy was performed, which shows that the 20 milligram addition of polyaniline showed the minimum resistance for the charge and ions between the positive and negative electrode. So further investigation was carried out in which the charge density was the scan rate, capacity density, and the scan rate was performed, and R square values were calculated. And similarly, the log of T current density versus log of scan rate values were calculated so that we can um, uh, be more sure that the electrochemical energy is thermodynamically feasible. So after making the electrodes and finding out the results, we have become sure that the maximum results were obtained for 20 milligram addition of polyaniline. Then by choosing this material as a positive electrode and porous carbon, activated porous carbon as a negative electrode, we made an asymmetric supercapacitor device. This is the schematic representation of this supercapacitor device. Then we perform the two electrode assembly in which we first optimize the potential window of the device. This is the cyclic voltammetry of the in the negative potential of the activated carbon, and this is the CV curve of the material that shows the maximum results. And after performing these tests and optimizing the potential window of the device, we perform cyclic voltammetry at various scan rates, galvanostatic charge discharge at various current densities, and continuous cycling and the capacity tension with respect to current rates and stability. Stability, our device shows very good stability up to 97.2% after 5,000 galvanostatic charging discharging cycles. Similarly, the device was further investigated after each 5,000 cycles to find out the effect of impedance on the device performance. And this is the Bode plot, which is also showing the similar effect of the impedance. And this is the famous Ragon plot, which is showing that our device is showing very good energy density and power density, and with respect to previously reported similar materials. Further, the capacitive diffusive analysis of the asymmetric supercapacitor device was performed to find out that how much the device is behaving capacitive and how much the device is behaving diffusive. So capacitive diffusive analysis shows that the more dominant factor was the diffusion controlled mechanism was involved in the asymmetric supercapacitor device, which shows that the charge, the more battery type collector of the asymmetric supercapacitor device, which is very good for high energy density and power density values. This is also the log of the uh, peak current density versus log of scan rate, and this is the current density versus scan rate graph. And these values shows that the R square value was very close to one, which means that the diffusion control mechanism was more involved in the device. So the conclusion of the work was that we've made four different compositions of the cobalt carbonate hydroxide hydrate with polyaniline, and the 20 milligram addition of polyaniline showed the maximum results for the supercapacitor electrode material. Then that electrode material was used as a positive electrode, and synthetic supercapacitor device was formed. The supercapacitor device shows the specific capacitance of 1308.4 farad per gram at 1 ampere gram. Moreover, the energy density of 35.1 watt-hour per kg with power density of 548.21 watt per kg was shown with cyclic stability of 97.3% after 5,000 GCD cycles. And this study shows that how the cobalt carbonate hydroxide hydrate nanocomposites can be used for energy storage devices applications. The paper was published in Journal of Energy Storage, and thank you very much. If you have any questions regarding this study, you can ask freely.